This module is about generating the random numbers with a computer. So interestingly, we can use this exact method to generate almost any other distribution, as long as we know their cumulative distribution function. So now let's see how it works. It works this way. We have the uniform distributed random number UI, and we want to generate some other random number. I call it xi e from a probability distribution f, and by f I'm denoting the CDF, cumulative distribution function, right? Again, what is f by x? It's a probability that your random number xi will be lesser or equal to x. That's all to it for CDF. And how do I generate this xi? Well, easy. If I have the set of uniform random numbers, I just plug them into the inverse CDF of this xi variable. Inverse CDF is like an inverse function. So here you see you take this CDF and plug your random number, and it'll tell you what's the probability. Inverse CDF will take the probability and generate the random number itself, like here, right? Why does this work? Well, because your uniform random numbers are from 0 to 1. It happens so that if you're plugging random numbers into the CDF, then on the output you will have uniform random numbers on the output, numbers from 0 to 1. Hence, if you take the uniform random numbers from 0 to 1 and plug into the inverse CDF, you are going to get the original random number. And how are we going to do it? So the easiest thing is when you have an inverse CDF, but let's start with a more difficult situation where there is no inverse CDF, and that's Excel for Poisson, right? Excel doesn't try to make your life easier than it should be. So we are going to look at what's going on with Poisson. So here in the sheet, I'm generating Poisson random numbers in column B. How am I doing it? This is how am I doing it. So Poisson distribution has one parameter, and that parameter is called, well, I call it lambda, but it can call it an average. So it happens so that in Poisson distribution, the lambda is equal to average, the mean of the random numbers. So I am setting it at 3, just arbitrarily. I put it at 3. And then I'm calculating the CDF of Poisson distribution. Cumulative distribution function. Well, for that, Excel was helpful. It gave me this Poisson distribution, and I can do the CDF. What Excel cannot do is two things. It cannot generate me the inverse CDF, right? Remember, we spoke just a minute ago that there is a CDF and there is inverse. So if you have inverse, it's very easy to generate random numbers. But again, Excel doesn't want to make your life very easy. So in Excel you have CDF, but you do not have inverse CDF. And forget about generating Poisson random numbers. That definitely is not in Excel. Okay, but the CDF is already good cumulative distribution for us. So if you put true here in Poisson dist function, it'll be a CDF. So CDF is already good. Why? Because see, I have this table now with CDF from 0 to 1, 2, 3, and so on. Poisson distribution, remember, it's a discrete distribution, meaning its outcomes are discrete, not continuous, right? Discrete numbers, 0, 1, 2, 3, and so on. It's whole numbers. Not only whole numbers, it's all non-negative integers, which means it's there's infinite number of outcomes. So I instead of going for infinite, I'm just looking at first 10, right? 0 through 9. But remember, if we keep going, like let's say 10, it's also a possible outcome, 11, 12, and so on. But I'm showing only 0 through 9. That's why my CDF of 9 is not equal to 1, right? Because it tells me that, oh, there's some other numbers, and there's infinite number of them. But again, I am going to ignore them. I'm just going to look at 0 through 9. Okay, I got the CDF. So what am I going to do next? Well, next, I have this random, let's say I have a random number, and then I have its CDF. So what I'm going to do is I'm going to invert. I'm going to use CDF and then get the random number. And that's what I'm doing here in column B. So look at what I'm doing in column B. I am taking the uniform random number from the cell, and then I am comparing, I'm looking at all the CDF values which are greater than that uniform random number, and of all of those I'm taking the minimum. So look at this. So let's say line 14, just randomly I'm taking line 14. What's going on in line 14? The following. We should go to line 14 on uniform, right? The number is 0.46. So let's get back to Poisson. 0.46, the smallest number, which is greater than 0.46, is 0.64. Right? 0.42 is less than 0.46. So the smallest number would be 0.64, and that's why I'm picking 3. Which line was that? 14. That's why I picked 3. So this formula is basically an inverse of the CDF. I'm going to show you. The formula which I just did, it's that formula is I built the inverse CDF pretty much. I didn't have inverse CDF in Excel. I have CDF though. So using that CDF, I was able to build inverse CDF. I didn't do it in the most efficient fashion. Of course, this is not a very fast implementation, and if you are using a better software, then don't do it. But you know, if there's no other way, if you don't have an inverse CDF but you have a CDF, why not? You could do something like this. So I generated 1000 Poisson numbers in column B. Interesting, right? So why don't I now build the build again the histogram, and that's what I'm doing here. Again, this is discrete distribution. That's why column G should be called PMF, probability mass function. So you see what's going on is like in average is about 3, right? We see that it sort of averages around 3, and that's what we're expecting. We can look at the CDF, we can look at the PDF, and if you want, you can compare it to theoretical good numbers. So here in a sheet called Poisson, I was able to demonstrate you how to generate the random numbers from Poisson, where we only have a CDF. We don't have an inverse CDF, but we have only CDF, and we were still able to generate Poisson numbers. Now let's look at the example of a Gaussian number. So Gaussians are going to be a little bit easier. Why Gaussians are going to be easier? Well, because for Gaussian distribution, look at this, inf, right? Norm inf. What is norm inf? That's an inverse CDF of Gaussian distribution. So we got lucky with Gaussian, right? So let's go into and look at the formula here. So normal distribution, or Gaussian, as it's called in physics and other hard sciences, in economics and finance, it usually is called normal. So this normal Gaussian distribution, it has an inverse CDF, inverse cumulative distribution function in Excel. How convenient, right? It's called norm inf. It has 3 parameters. I believe it has 3 parameters, right? So the first parameter is that uniform number which you plug into it, the number from 0 to 1. Then you plug the average, mu, right, mean, and then the third parameter is standard deviation. Now, pay attention that in Excel doesn't want to do anything easy for you, right? In Excel, the sigma is the standard deviation, While if you remember, in econometrics and in finance, oftentimes when we write the normal distribution, we will write it as mu sigma square. So remember, in notation, in like mathematical econometrics notation, when we denote a normal distribution Gaussian, we use variance, while in Excel it's a standard deviation. Somewhat makes, maybe it's a little more even intuitive, I would say, if you're a business analyst, but just be careful that in math notation it's variance, and in Excel it is it's standard deviation. But then it's very easy, right? So unlike with the case of Poisson, where we had to build this inverse CDF manually in the table, in normal distribution case, Gaussian case, we are given this inverse CDF. Excel has it. Let's see what happens. Well, we can look at the very first maybe cell in column B. All we're doing, we're getting normal inverse Gaussian function, right? And then we're plugging that uniform random number from the first sheet, from uniform sheet. Let me actually increase it a little bit. Okay, right. So we're plugging the uniform random number, and then we're using what we're using. We're using mu and sigma, standard deviation, in column D. Once we've done that, I again generated 1000 random numbers, Gaussian random numbers. Now I'm building the histogram again using the same basically logic as before. I'm building the histogram in columns E, F, and G, right? So column F is CDF, cumulative distribution function, and column G is PDF. Well, here, interesting, I don't have to scale because my bins are stepped at 1, 0, 1, 2, 3, and so on. So I don't have to scale PDF anymore. Okay. Right. So how do let's use a proper formula. Actually, we have to. Yeah, we don't have to do it here because again the bin step size is 1. But in Poisson, again in Poisson we don't have to do it. I'm just trying to be careful here, right? And here, okay, right. So in Gaussian, then I'm showing you this typical bell-shaped PDF of a Gaussian distribution, and its CDF also has this S-curve type of shape. Again, you can look at the numbers and just check that it matches the theoretical numbers. So this was uniform Bernoulli, Poisson, and Gaussian, right? Bernoulli, we did it intuitive way. We weren't trying to do any theory. In Poisson, we applied the theory, or at least the formulas which I showed you in the beginning, and we had to do some extra step of converting the CDF into inverse CDF, while in Gaussian, luckily we had an inverse CDF ready for us, so we didn't have to build it ourselves, and we were able to generate Gaussian random numbers. Now, as an exercise, I'm suggesting you would try to do the same for binomial distribution with parameters n and p in column D, in cells D1 and D2. Right, so you can use CDF and PDF the same way for the histogram in columns EFG, but I'm suggesting for column B you plug your own formulas, do a little research on Excel, and find out whether there is like in Gaussian case, whether there is a convenient inverse CDF for you for binomial in Excel. If it's not there, then you will have to do what I've just done in Poisson, right? Build a table-based inversion of the CDF. And on that, I'm going to wrap up this module. It was generating random numbers with a computer.